there's a lot of fundamental ideas in the distributed training community, in the optimization community, that are yet to be applied to the settings that all of us are working on right now.
I think in order to kind of achieve that super high scale requirement for the next era of AI systems, we need to also solve the verification problem, and solving the verification problem increasingly kind of results in, solving the reproducibility or determinism problem.
Basically, what has been shown by Google Deepmind, and we replicated it basically, right, is that the approach works really well with like scaling to like 500 steps, for example.
One of the ways that the future training would go is that you would not have a type of like synchronous training where every node has the same model, basically. So in some sense, DiLoCo is one of the first ways of like partially synchronizing. Only the next step is to not synchronize.
If low-band communication works, I could just build data centers that don't have infinite connections, have different types of cooling, that are all in the same place, instead of having 100,000 GPUs in one place, maybe 10 small ones with like 10,000 each.
During a conversation on X Space, I talked with Max Ryabinin, Bowen Peng, Grieve, Johannes Hagemann, and Mohamed Baioumy. Our conversation centered around the current capabilities and potential advancements in decentralized deep learning. We explored various methodologies, techniques, and the promising trajectory of future research in this field. Thanks everyone for joining. Welcome. It's great to have everyone here. I'm Christine. I'm from the Gensyn team. We have Max here, we have Bowen, we have Harry, Johannes, and Mo will join us as a speaker in a minute as well, hopefully. All of them are very actively working and contributing to decentralized deep learning. Some of them are authors of very notable work in the space. For example, the Swarm, Learning at Home, or Hivemind. Some of them have done very interesting experiments and obtained very promising results. You might have heard of DisTrO and OpenDiLoCo. And there are also some who have worked on very practical implementations, such as Petals and Exo. We'll have plenty of opportunities to touch on all of these in the next hour. And I will try my best to help facilitate the conversation today. So with this, let me pass on the word to the other speakers, and maybe everyone can say a few words to introduce themselves. And yeah, feel free to mention any relevant background or interests. Who wants
to? Cool, I'm happy to kick it off. So I'm Harry, I'm a co-founder of Gensyn. The kind of Gensyn protocol exists to network together all the components required for machine intelligence. So our core focus just now is on networking the kind of requisite compute resources together to train the next era of ultra high scale machine learning models. My background prior to co-founding Gensyn with my co-founder Ben was in applied machine learning. So I led a research team for a few years, which focused on predicting disaster events. And when I was doing that, we burned a lot of money on compute, and it kind of exposed me to the problem a few years ahead of the kind of market waking up to it with the post-ChatGPT boom in compute demand. So yeah, that's me.
Awesome, thank you, Harry. Maybe Johannes, do you want to go next?
Yeah, for sure. Nice to meet you all. I'm Johannes, one of the co-founders of Prime Intellect, and what we do is we basically aggregate global compute resources and work on research for actually making it work to do distributed training across different clusters of GPUs, right? I've done the OpenDiLoCo work and now the Intellect 1 model recently, we probably enough time to talk about those later.
Yeah, awesome. Maybe Max?
Sure, I can go next. Hi, everyone. My name is Max. I currently work at Together AI, and I've been working on different angles of decentralized deep learning for, well, quite some time, to be honest. So we started working on this even before GPT-3 was announced. So one of our first ideas was to try decentralized training of mixtures of experts. Since then, we've conducted successful collaborative deep learning experiments. Like back in 2021 with Hugging Face, we worked on the deadlock method. So we trained like probably one of the first collaborative experiments for pre-training LLMs. Later that year, we participated in the training transformers together experiment at New Rips. Also, I've worked on the swarm parallelism paper as the first author, which is kind of like the work for scaling pipeline parallel training to decentralized setups, to clusters, to all over the world and volunteer settings. And also the pedals work, which is probably one of the most well-known ones, that offers everyone a way to participate in running large language models for inference, also in this global context. At that same time, we've been developing a framework, an open source framework for deep learning called Hivemind, which is based on PyTorch, and that has been used in virtually all of the works that I just mentioned to you. So yeah, that's basically it. And happy to meet all of you here.
Awesome. Thank you, Max. Very excited to dive more into all this amazing work. And then Bowen, do you want to go next?
Yeah, hi, thanks. Hi, I'm Bowen. I'm the chief scientist at Nous Research currently. And my background is actually in machine learning and computer graphics. I've done a master's at Mila and Ligum, which is a computer graphics lab. And then after that, I've just found interest into LLMs, and then I joined Nous Research to do research on basically anything that could accelerate open source AI, open source machine learning, and like just everything in general. So now I'm working on distributed training, especially how to make the optimizer itself make a compromise-free optimizer that matches like or even beats ADAM, that can massively reduce the amount of communication. So like basically if you want to train across the internet, you cannot transmit the model weights ever, basically. Like if you just transmit the model weights, then you will wait like hours, right? Like if you have 100 GPUs and you have to transmit 10 gigabytes, that's like hours of transmissions. So basically accelerating this is a major block right now for open source AI. And then if we can solve this fully, we will be able to match like centralized, like big clusters, right? You will be able to have this fully decentralized training runs. Yeah.
Yeah, thanks, Bowen. Very excited to dive deeper into your work as well in a bit. Let's see. I wonder if Mo is already ready. I think he mentioned that he's going to try to sign in using a different device. I think we can continue and get started. And when Mo is here, we'll give him some time to also introduce himself to everyone here. So yeah, I'm very excited to dive into this conversation with all of you. Decentralized deep learning is so interesting. In the past decade, we have witnessed a very significant rise in the scale of AI models, and many of the popular models have outgrown the capacity of a single device, which makes it now very necessary to do distributed training across multiple devices. So before we dive into all the details, maybe let's first take a moment to talk a bit about what the state of things is right now. So I don't want to put you on the spot, Max, but I know that you were the author of many papers that kicked off this space, such as you mentioned learning at home, Hivemind, Swarm, and more. Perhaps it's a great place to start with you. Can you talk a bit about what the state of things is right now? Like, what can we do today in terms of maybe model size or performance, and how did we get here?
Yeah, sure. So I want to give a disclaimer by saying that I might not be aware of the latest research that's done in the area. I try to keep up, and hopefully, if any of the folks think I'm missing some crucial relevant work, let me know. But overall, in terms of decentralized training capabilities, there are multiple things that are definitely possible at this point. So one thing we're seeing is that data parallel training, so basically training large but not very large models over larger data sets, is quite scalable. And given the interest of the machine learning community in having smaller and maybe smaller models that are easy to run for inference or even on device, that makes a lot of sense. So in terms of data parallel training, people have done experiments back in 2021 about 1 billion parameter models. And right now, for example, with Intellect 1, we're seeing even the scale of 10 billion, which is reachable. So thanks to the folks from Prime Intellect, we're seeing them make progress. And we're seeing a lot of interest in this area from other angles. Also, I have to point out the DiLoCo paper from Deepmind, which kind of approaches a similar angle and which inspired OpenDiLoCo as an example. So that's about the data parallel angle of things. There is also a question of how large of models can we train if we scale out even more. So let's assume that models are not trainable on a single device. In that case, I believe that, the sky's the limit, but not so much. There are also some physical considerations at play. Overall, in case of swarm parallelism, we were able to do things that would roughly amount to 12 billion parameters very easily. And that was basically with the previous generation of hardware and using the interconnects that are not quite comparable to what you would get in decentralized but not volunteer, so closer to the cross-cluster setup. I think we should expect that it's possible to probably not within an order of magnitude, but definitely increase the size of the models quite substantially. So probably going beyond 10 to 20 billion parameters is very much possible. And depending on the capabilities of your infrastructure and the methods you apply, maybe even more.
Thank you, Max. If none of the other speakers have anything to add, then maybe maybe even before we dive into the specific techniques, I think Max mentioned some things about data parallelism. Maybe for the listeners, maybe we could first briefly go through how you actually do these distributed training, what kind of parallelism techniques are out there. Maybe Harry, do you want to maybe give everyone a brief introduction to that before we dive into the specific methods?
Sure. So classically, prior to doing this in decentralized contexts, and when most people say decentralized, that's distinct from distributed. So distributed, for example, would be how all of OpenAI's GPT models were trained. They were trained across distributed hardware, but inside a kind of central location. When we talk about decentralized, it kind of touches on the point that Bowen said, it's over the internet. So they're kind of in very distinct locations with distinct owners usually. But a lot of the kind of techniques used in the distributed setting kind of crossover. The kind of core split you can think of in terms of techniques is between data parallelism and model parallelism. Data parallelism looks like taking the kind of same models and putting them on different devices. So if you had two RTXs and they were 24 gigabytes and you wanted to basically train on, I guess, a large model which could fit on both the GPUs individually. So it was, significantly smaller than 24 gigabytes in size. You could speed up the training by splitting the data set in half and putting half of it through one and half of it through the other, and then combining the results at the end. That's the kind of essence of data parallel. The kind of second split is model parallel. The kind of most intuitive and easiest example of that would be like pipeline parallelism. So that's where, if you think of a neural network in its layers, if you just imagine in the simplest case, like chopping it in half. So you've got the kind of first chunk of the model, the data goes through there on GPU 1, and then the kind of next half of the model, the data is then sent to another GPU, or the outputs, I should say, from the kind of intermediate activations are sent to another GPU, and then it goes through that one. It basically allows you to get a model which can't fit on one GPU and split it over multiple ones. There's then concepts like tensor parallelism, which basically split the weights within a layer across GPUs. So for a given layer, you take matrices which were used for training or inference on one of the weights, and then you'd split that across different GPUs. And then the final one, which kind of like loosely fits under model parallelism, although it's kind of more architectural, but it's relevant, is expert parallelism. And that's the idea of the actual architecture of the model itself being designed in a way which naturally parallelizes across different devices. If anyone's ever used Mixtral, or some of the earlier mixture of experts work that Max focused on a few years ago, basically the models are designed to train across different bits of hardware, and then the results of those kind of individual experts on each bit of hardware are then combined at the end. So usually a subset of them are selected. They have a routing layer at the top and an aggregation layer at the bottom typically. And the idea with expert parallelism is that each kind of expert in the system can learn a specific kind of concept or idea. It's very common for expert parallelism to actually be used inside large models. So things like GPT-4 are essentially believed to have expert parallel layers inside them, as are some of the earlier kind of transformer architectures. So yeah, to summarize, two main kind of categories. One is data parallel, you just split the data set across GPUs, and the second is model parallel, where you can do it tensor, pipeline, or expert, but expert's a bit of a kind of fuzzy category. That's the kind of concepts applied in a distributed setting. They also all extend to a decentralized setting.
All right. Yeah. Thank you, Harry, for giving us this brief summary of these parallelism methods. They help us to shard the model or the data, but there are probably trade-offs, right? It helps us do distributed training, but probably there's also more communication overhead. And I guess that's probably what some of these methods, like DiLoCo or maybe also DisTrO, are tackling. Maybe Johannes and Bowen, do you maybe want to talk a little bit about what are the trade-offs of using data parallelism, and how do the methods that you used help address those trade-offs? Up to
Yeah,
you
sure.
who want to go first.
I can jump in and take that one. With data parallelism, we basically train our models on different clusters of GPUs, right? So we have our complete model weights and optimizers and gradients on there, and train the model separately just on different data. In your usual data parallel setting, you have to basically sync your gradients after every step of training, basically, which is not the most amount of memory requirements compared to other maybe techniques, right? But it's still quite a bit of data. So if you train, for example, a 10 billion parameter model, the gradients are maybe an FP16 20 gigabytes. You would have to sync 20 gigabytes every step, basically. And then there are different approaches, either to, for example, compress those gradients heavily but also other approaches like those local SGD approaches like a DiLoCo, where you basically don't communicate those gradients too often, basically. So how the DiLoCo approach works, for example, is that you have an inner optimizer and outer optimizer, and your inner optimizer is basically just your usual distributed, your usual like training, basically like a W optimizer, for example, right? And you do your training locally on those islands of devices, and then you only sync them not every step, but maybe every couple hundreds of steps, right? So and then you have an auto optimizer state every hundreds of steps where you basically sync those gradients, right? And the DiLoCo approach is a momentum optimizer to do the auto optimizer step, and there you all reduce. You need to sync all those gradients, right? And then sync your do the update step and continue training on the islands of devices. And basically what has been shown by Google Deepmind, and we replicated it basically, right? Is that the approach works really well with like scaling to like 500 steps, for example, right? So you can do local steps of 500 and then have to sync every 500 steps, and can reduce the communication requirements by 500 through that, right? Obviously also some limitations in that still to like schedule more workers and stuff like this. But happy to jump into the details more later.
Thank you, Johannes. I saw that you did some experiments and there was OpenDiLoCo. Maybe this is a good timing to just double click on it a little bit. I know that you probably had the DeepMind paper describing the DiLoCo, but you didn't have the implementation. So I was wondering, like, when you tried that out, were there any surprises that you encountered? Any things that you didn't foresee or expect? Could you maybe tell us a bit more about that?
Sure, yeah. I mean, from surprises, it was just very much a hard engineering challenge to get it done, right? So we did the initial release with OpenDiLoCo, I guess, like 3-4 months ago, where we replicated it on top of Hivemind from Max, right? We're able to reproduce it and scale it to the 1B size. That was great. And then, for the last couple of weeks, we tried to scale it even further, right? So, and also made some improvements on the algorithmic side of things, right? So one of the things we could discover is that it's very easy to, for example, it performs well to quantize the pseudo gradients that you send there every hundreds of steps. So we've done this on the smaller size and evaluated it. If you can quantize those pseudo gradients, which are usually in FP32, right, to FP8, to get another 4x reduction every hundreds of steps. And that worked pretty well. It's a 150 M to 1 billion model size. So we applied it now to our 10B one, right? So that was one of the surprising things we've discovered there.
How similar is the quantization of those pseudo gradients to the work of DisTrO from Nous? Because I think like a lot of the benefits there are from reducing the kind of communication requirement between the different nodes at that stage, right?
Yes, I think Bowen needs to jump in and tell us more.
Oh yeah. Do you want me to talk a little bit more about DisTrO? Because the thing is that the DisTrO method is like, I'm under NDA, so I can't like delve into too much of the details. But like I can talk about like some of the differences, and also like DisTrO is it's completely different in the sense where it doesn't use. It's like another optimizer. It's a new way of thinking about how to train neural networks. So usually in traditional training, when you do data parallelism, what you do is you assume that every model should stay the same, right? You're trying to use every GPU to train a single model, right? And this single model has to be synchronized somehow across thousands, millions of GPUs. And the only scaling you can do is just separate the data and then accelerate the training by using more and more GPUs, because every GPU can train, let's say, on 1 billion token every step, like every node, for example, not 1 billion, let's say 100 million. And then you scale this across like thousands of GPUs, and you can train a large amount of tokens per step. And this is data parallelism, basically. And usually people accelerate training using data parallelism because it's the easiest way to scale. When you scale across the model size, it's just, you increase the latency because every GPU has to wait for other GPUs, right? They can't do it in parallel. Like tensor parallelism can, in some ways, parallelize the compute, but you still need to do it like sequentially, like one after the other, in some sense, in some of the aspects. So the best way of doing it is with data parallelism. And then we looked at data parallelism and found that the biggest bottleneck is just transmitting all of the gradients, right? Like every step you need to synchronize the gradients. And basically with DiLoCo, what they found is that there is a way of not doing that every step. You can actually delay the synchronization. You can delay it for 200, 500, or 1,000 steps. And that would significantly decrease your bandwidth requirements. But one of the major disadvantages of doing it using two optimizers, an inner and an outer one, is that it's very difficult to tweak. Like we actually, the people at Prime Intellect have done a large amount of the work of tuning the OpenDiLoCo method to make it train, because otherwise, like, it doesn't work out of the box. Like, it doesn't. It's very hard to find the good hyperparameters, and we haven't found them. But like at the same time, before OpenDiLoCo was released, we already was working on. Actually, we were looking into something called Zeroth-order optimizers. Like that was actually before that I started working on DisTrO. I was working on Zeroth-order optimizers because that is a way of training neural networks without gradients, right? So if you don't need to share the gradients and you can train a neural network without gradients, then you would sidestep this problem of data parallelism, right? Because you don't have gradients. And the thing you synchronize is very fast. It's very small in Zeroth-order optimizers. You just synchronize the seed, basically. It's a single number. And as such, like these types of gradient-free methods could be one of the ways to scale distributed training. But the problem is that Zeroth-order optimizers are very slow. They're very, very unoptimized. It's very, very hard to pre-train. We've tested fine-tuning and it works. Basically, it does work, but for pre-training, it doesn't. Like the network doesn't converge, basically. So then we looked at alternatives and we found ways of just like getting outside of this paradigm where people always assume that we have to share everything every step, right? It's like, can we find an optimizer that doesn't require you to share everything? Like never. You basically never share everything. You always share only a small amount of data between all of the nodes. As such, all of the nodes are basically training different models, right? They're kind of training different models because you will never be able to synchronize a 3 trillion parameter model if you don't send 3 trillion numbers. You can quantize, right? Like there's ways of quantizing and reducing the size, but you still cannot go under 3 trillion. Like 3 trillion bits is the absolute minimum. If you have a 1 bit model, then 3 trillion bits for a 3T model is the smallest amount you have. So then as we looked into quantization and other methods, we realized that it would never be possible basically to distribute a 1 trillion size model across the internet. Because no matter how you try to synchronize, just the fact of synchronizing would slow down the training significantly. So I think one of the ways that the future training would go is that you would not have a type of like synchronous training where every every node has the same model, basically. Like in DiLoCo, it's already almost like that, right? Like the intercepts are different. Like in every node, when they're training, the intercepts are not synchronized. So in some sense, DiLoCo is one of the first ways of like partially synchronizing. The only thing left, I think, is just to like the next step is to not synchronize everything, basically, and we're still working on that with DisTrO. It's been a challenge because it's very a problem with this is that model divergence becomes a problem now. Like the difference between DiLoCo and DisTrO is just that, like, effectively DisTrO doesn't synchronize ever, while DiLoCo does synchronize after some amount of steps. The effective network compression is similar, but in DisTrO you always transmit every step, compared to DiLoCo where you have to like not transmit and then transmit everything at the end, right? That's kind of like the trade-off, I think. DiLoCo is more bursty, so I don't think DisTrO and DiLoCo they're completely they're like completely different things. I think they could be used together, and for different network capabilities, you would prefer DisTrO or DiLoCo. Like, it's not one or the other, actually, because you could use them together.
Yeah.
Yeah. There's a lot of things to say about the differences, but I mean, maybe I'm getting sidetracked.
No, that's great. Thanks, Bowen. That's an interesting view. I would love to actually hear if Johannes would have the same thoughts about how he sees this. But maybe before we go there, I just saw that Mo joined the conversation. Maybe let's give Mo a moment to maybe also introduce himself. I'm really happy that your audio worked out, Mo. Great to have you here.
Yeah.
Awesome.
Can you hear me?
Yes.
Well, sorry for being late. Usually Zoom decides to update right before the meetings, and today for some reason it was Twitter. And thanks for the people who pinged me to try and come on. Very briefly, my name is Mohamed. I studied in Oxford, did a PhD in robotics and AI, and I work now at a company called Exo. And at Exo, essentially what we're trying to do is make it really easy for you to run models on edge devices. So you want to run the biggest models, let's say Llama 405B. Normally you would need like multiple GPUs for it. With Exo, you can just look at a few laptops together and you can just run it yourself at home privately. That's TLDR. Is it okay if I ask a question to some of the other speakers from what we were just saying earlier?
No, before you joined Mo and in the first 50 minutes, I was just saying, like, let's treat this as a space or online room where we all are hanging out and talking about distributed or decentralized deep learning. So definitely feel free to join this conversation and help and respond to one another, ask questions, let your curiosity run loose.
Yeah, so maybe just to make sure I understand this correctly. So previously, if I wanted to train a model, like back in the good old days, models were small. I just have one machine, I put my model on it, I train my data, and life's good. And then over time, models became really big, and then this will be very time consuming to train everything on a single machine. So then I could now go and get like a rack of GPUs. And these GPUs have these very fast interconnects, like the NVLinks, for example, basically making 8 GPUs like one big GPU. And what I would do is I would have all my data. I have these 8 GPUs. I will give each GPU a copy of the model, and then each GPU will like separate data. And now instead of one machine training, now I have 8 training at the same time. And these GPUs have these very fast interconnects, so they can just quote unquote synchronize at the same time. So I have a copy of the model, 8 GPUs, each have some data. They each train for one step. Now each model is slightly different, and then I can like average them out again. So they're all the same again. And I keep doing that. If I now go from the setting of like, I don't have the NVLinks and I have like Wi-Fi or something, this would be very inefficient, because probably what will end up happening is my model are training for 1 minute and they're synchronizing for like 10 minutes or something. So effectively, I'm actually worse off training on 8 GPUs than 1 GPU, because for them to be back in quote unquote in sync takes so much time. So just the question I wanted to get to is like, Now, different approaches to solve this problem, quote unquote, solve this problem. One is DiLoCo, which, as I understand, is instead of training one step and then averaging out, I'm going to train for like 100 to 500 steps. But essentially, I'm going to end up with the same model again. So like every 500 steps, each model trains a little bit independently. They're all slightly different, and I'm going to average again. So now, instead of training for 1 minute and then synchronizing for 10 minutes, I will train, I don't know, for 5 hours and then synchronize for 10 minutes. So now it is better to have more devices, unlike before, if I synchronize for so long. What I'm curious about is like some methods like DisTrO is you never quite synchronize the whole model. So now I have 8 GPUs and each model is slightly different. Don't synchronize everything. I just send a little bit of information. I was wondering if you found other interesting ways that this is useful. This is basically essentially now 8 models who are all roughly, I assume, similar performance, but slightly different, kind of an ensemble. Is this, for example, useful in other things? Potentially like having a Bayesian model or using that kind of information to reduce hallucination?
Okay, so we haven't really investigated this much because everyone's like full force on trying to make the method as like scalable as possible. And there's also like problems such as verification, and like if somebody can break the training run, like adversarial attacks. So there's like so many problems we have to solve for decentralized training to work that we haven't yet actually looked at why does DisTrO work. I'm hypothesizing that DisTrO works just because there's a trade-off. Like there's actually a benefit of letting the networks diverge somewhat, because I just think intuitively there's probably a benefit to it. But then transmitting a little bit of data like actually harms convergence, but letting them train like by themselves and diverge a little bit improves convergence. And somehow the sum of those two cancel out, like in the loss curves, right? Because what we've seen is that if we let them diverge too much, that means if we reduce the communications to like a very small amount, then the training would start to like not work. They would start to just train independently, and the pseudo gradients, kind of like the things pushing the models together, doesn't do anything basically, because it's just the models are way too different, right? But if the models are exactly the same, we've tried that. We've tried DisTrO by synchronizing, like we synchronize everything, then use DisTrO. It's worse. It's not better, like because you're transmitting less information every step, right? You're still losing some of the. It's like when you train using some amount of data, right? The data is finite. Your model is bigger than the data, right? So in some intuitive way, you should probably be able to transmit a part of the model, like only a small subset of the useful thing that the model trained to other models. You don't need to transmit the whole model. Like that's I think that's the core idea of DisTrO, because when you the mini batch size of
I also assume
are very
the
small.
model is
They're
somewhat
very
similar.
small. Yes. Sorry. Go ahead.
Oh, sorry. I was gonna say like one thing that might be happening is like when you synchronize the whole model and then use DisTrO, it's worse. It might be there's some kind of regularization happening. It's like you're regularizing based on like gradients from like another batch, kind of.
Yeah, kind of. That's what I think it's happening, because otherwise it doesn't make sense. Like, because when you transmit less information, it should just converge slower, right? Like DisTrO, in some cases, we don't want to claim that, because that's kind of dangerous when you claim an optimizer beats ADAM. But like in all cases where we tried, it does beat ADAM. But we just don't know why. But we don't want to claim that. Like, we don't want to claim that yet. Like, just assume that DisTrO is like as good as ADAM. The DisTrO ADAM W version is as good as, but it's just, there must be something, right? Like inside of letting the models kind of search, basically. It's kind of like a search. You have this trade-off. Yeah,
the other interest.
Yeah, Mohamed, go ahead.
Oh, I think.
Yeah, maybe. I see that.
I don't hear.
Up for a while. Maybe.
Is it me or?
Oh.
Yeah, I think it's not only you. I just wanted to offer a quick comment on the difference between methods, because indeed, as if I understood Bowen correctly.
Yeah, I don't hear anyone, I think.
All right. Can someone hear me?
I can hear you, Max. Feel free to go on. I'll chat Bowen.
All right.
Is my audio broken, or is it nobody's talking?
All right. I hope I'm not going to interrupt you that much, but I wanted to offer a bit of a perspective on different methods for distributed training, because indeed some methods for data parallel training, like DiLoCo, like standard stochastic gradient descent, do have to exchange the entire model. We've progressed a lot in the direction of not requiring that. So basically all of pipeline parallel training, all of like tensor parallel training, the benefit is that you are able to train much larger models, specifically not by exchanging the entire sets of parameters. So I think we've even seen some works which attempt to combine this with asynchronous training. So I just looked up a couple of papers, and I think one of the first ones was called PipeMare, and it was released back in 2019. So basically before this, a lot of the work that we've been discussing has started, and we've seen some very promising results in this area. So one thing I wanted to highlight is that the challenges that we're discussing right now, like the communication overhead, all of them were quite well known in the standard HPC / distributed training community for quite some time. So, and in many cases, it helps to draw inspiration and sometimes directly apply the methods that have been proposed for those new purposes, like training across data centers or even training in the volunteer setting. So a similar example is both asynchronous data parallel training, which also doesn't need to happen. So I believe Google have kind of pioneered this entire direction. Some people will say in 2011 with HogWild SGD. Some people might say that this was tried even earlier. And the same thing basically applies to DiLoCo and other approaches which are under the broad family of local SGD methods. So the first paper on local SGD was introduced back in on the theoretical analysis, I think in 2018, I cleared 2019. And the fundamental idea behind it has basically stayed unchanged. I'll be happy to stay corrected here, but what I wanted to tell you is that there's a lot of fundamental ideas in the distributed training community, in the optimization community, that are yet to be applied to the settings that all of us are working on right now.
Thanks, Max. Mo, I know that you wanted to speak as well. I think you and Max spoke around the same time. Did you want to respond on this as well?
I forgot what I wanted to say. It's fine.
No worries. How about Bowen? Are you back? Is your audio working?
Yeah. I couldn't hear anyone. Did I interrupt anyone? I'm sorry if I did.
I think you're good. I think it went well.
Okay.
Yeah, all right. Oops. Yeah, I think that was a very interesting to learn more about these different methods. Maybe I think we learned a bit about DiLoCo, we learned a bit about DisTrO. I would love to maybe dive a little bit deeper into Swarm as well. How does Swarm tackle decentralized training? Or how does it help? What are the trade-offs? Could you maybe talk a little bit about that as well, Max?
Yeah, sure. So I believe Harry gave a very good overview of different methods for distributed training. So, and some of them are closer to the data parallel side of things, like DiLoCo, or for example, if I understand correctly, DisTrO, but maybe my understanding is wrong. And Swarm is basically on the other side of the spectrum, if you view it as a spectrum. So instead of splitting the training across different parts of your data set, you instead slice the model into smaller pieces, well, basically usually by layers of a multi-layer model, and you put all of those layers on different devices. In some cases, you have multiple devices serving one layer, and they work all in the data parallel setup. But basically what happens is that you have a very long pipeline of layers that you have to go through to make a forward pass and then the backward pass. So this is the basic idea behind pipeline parallelism. And at its core, swarm parallelism is nothing more than that. So my previous thought was basically expressing the idea that techniques like pipeline parallel training or other approaches from distributed training, sometimes they are very much directly applicable to the decentralized setting. And there are a couple of changes or a couple of observations we had to make to see what makes pipeline parallelism effective in this context. So one idea is that, as Bowen has pointed out, if you try to train very large models over the internet, you absolutely don't want to exchange their parameters, because the size of parameters can be very large at like the GPT-3, 4 or something scales. So what you do instead is you send only the intermediate activations between layers, and all of the parameters never leave the model, apart from the situations where someone joins the network and then has to download them. So in this case, you are basically saved from having to synchronize the parameters across the entire collaboration every time. You still have to exchange them across smaller groups of peers that are all responsible for the same set of parameters. But this is relatively less impactful, because different groups in that case can participate in updates at different points in time. And another idea that was quite important to us, well, one or two important ideas that were quite important to us were that, first of all, sometimes you can afford or tolerate a very tiny bit of asynchronous training without impacting the capacity, like without impacting the convergence properties too much. So I believe that one of the first recent results on this was shown by Microsoft in one of their uploaded training papers. Basically, you can delay your stochastic gradient descent steps by one. So like you can have slightly stale gradients, and that will work reasonably well. There is also a lot of theoretical studies that explain why this is actually a good thing to do, or why this is not a too bad thing to do. And this is what helped us achieve a better overlap of communication with computation in this setting. There's also another idea, which is basically about trying to compress the activations or gradients. We've done a bit of research in this, at this angle for Swarm. I wouldn't say that we achieved the best possible degree of compression, because it's very difficult to keep up with quantization research, especially for activations and gradients. I haven't seen a lot of research in this area, but would love to. And from what we observed is that there are some very low-hanging fruits on that side as well. So as long as you are willing to kind of flip the direction of communication and exchange activations or gradients instead of your parameters, you are suddenly able to do a lot more very interesting things. And that's basically what led us to developing Swarm.
Thanks. Thanks, Max. That's really interesting. It also seems that Swarm really addresses fault tolerance, which is also very important in decentralized training. I'm very curious, where everyone sees these methods going next. Do we think certain methods can be combined, or where are the biggest improvement that we can make? Does anyone have any thoughts on that?
I can start if you don't mind, because I've been following with a lot of interest the research directions that different groups are going into these days, and there is definitely a lot of potential to combine different approaches, especially with what we're seeing with DisTrO and DiLoCo on the data parallel front. But there is also a lot of research that is yet to be incorporated in this broader setting. So I think overall, having the idea to communicate as less frequently is probably a very interesting area to tackle, because a lot of standard distributed training setups, which is designed for high performance clusters, is not working really well for those setups. So I guess this is something that might be interesting to explore and maybe combine some of the methods to achieve the best results. We've seen some works in the area like Cocktail SGD that try to combine different methods for communication efficiency for compounding gains. So I don't see why this this angle cannot be continued. Yeah, I believe Harry has raised a hand.
I'd agree with all of that. I'd also say when we think about it at Gensyn, we think a lot about the neural scaling laws and just the idea that increasing scale is one of the kind of core prerequisites for achieving something at least approximating AGI. And to get to that scale, you need to fold in devices which kind of don't look like your typical data center hardware. So similar to the stuff that Mo's done with MacBooks and Apple hardware, but then also just beyond that to the kind of longer tail of data center chips, etc. A lot of those devices are untrusted, and as a consequence, you end up in the kind of you end up with a verification problem. How do you verify that work on an untrusted device has been faithfully executed? And a lot of the kind of work we do sits around that. It sits around how do you achieve that trust, and often it comes down to the kind of case of reproducibility. So a lot of the kind of particularly asynchronous parallelization frameworks, they can't achieve reproducibility because they require because you can't predict, you can't kind of time the way that the graphs are combined because of the fault tolerance assumptions, because some nodes disappear, etc. And then that's just at the framework level. When you go down to the kind of on device level with the GPUs and their platforms like CUDA and trying to achieve cross-device, bitwise identical reproducibility, that's another kind of huge issue. So I think in order to kind of achieve that super high scale requirement for the next era of AI systems, we need to also solve the verification problem, and solving the verification problem increasingly kind of results in, solving the reproducibility or determinism problem. So I would throw that into the ring as a kind of a noble research area.
Yeah, can I add something? I think the verification problem is it's going to be one of the hardest, if not the most hard of everything, because solving for convergence is already, even with OpenDiLoCo, it's proven, right? The model will converge. It's maybe a little bit slower, and it's just engineering issue. You just have to figure out the best hyperparameters, how to scale, and after a few years, people would be able to use either a combination of DisTrO and DiLoCo to train huge models with Swarm, right? You want to scale up in the data side and the model size, because smaller GPUs like 3090s, you can't fit a 4 trillion parameter model in it. So of course we will have to use tensor parallelism or model parallelism methods like Swarm in conjunction with DisTrO, DiLoCo, and all of the data parallelism methods. Together, they will be able to train in the near future, sizes up to 300B, 1 trillion. I think that's possible. But one of the biggest blockers will be verification, because verification will require either the triple amount of compute if you want to have agreement, right? You want to have 3 votes, that will triple just the compute. That's very bad. Or you would have to bake in somehow verification inside of the training. So somehow have a way of verifying that the gradients are correct and they're not being messed with. Just proving convergence cut it, because people could be adversarially attacking the model by at the same time reducing the loss and also injecting like potentially bad behaviors, right? So yeah, like that's one of the hardest problems that I can see. Yeah.
I think, the threat model matters a lot in the kind of the hardest case where you can't, have a single kind of tensor put through the training loop, which is malicious. It becomes very challenging. If your kind of threat model is you're just trying to protect against like lazy trainers, so you just want someone to have like an expected value of cheating, which is negative. In other words, like they're more likely to get caught and lose money than not. It becomes easier. But certainly, the kind of like needle in the haystack problem of trying to prove that someone's slipped like a prompt or an image or something through a model in a verifiable way is really hard. Mo, I think you've got your hand up.
Yeah, like the verifiability problem obviously needs to be solved if I'm crowdsourcing compute and there are malicious nodes and stuff like that. I was curious, like, if the technology works for low bandwidth training, I could train stuff without these very fast interconnects. Like, what else becomes possible? One thing that comes to mind, I'm curious what the rest of people think here, is just I could just build cheaper data centers. Like, if low band communication works, I could just build data centers that don't have everything connections, have different types of cooling, that are all in the same place. Instead of having 100,000 GPUs in one place, maybe 10 small ones of like 10,000 each. And like, what else becomes possible if like low bandwidth training like is efficient?
I wanted to offer a thought on this because I've been thinking about like both low bandwidth and heterogeneous training actually a couple of weeks ago. One research area that is quite interesting to follow in like a very similar spirit is all of the work on model merging, like post-training merging and model editing as well. So if you've read the works on like branch-chain merge and some other ideas in the field, it is quite clear that we are able to reap the benefits of trying to train multiple like models in parallel and then kind of aggregating the results, but not in the standard like distributed or data parallel way. So this can be done even at the end of training or in very few iterations throughout training. Yeah, sorry, I think you raised your hand. Is there something you wanted to? All right. So, and in terms of heterogeneous training, there is actually a lot of interesting research that can be done. So in DiLoCo, for example, we tried to tackle this because of very natural constraints. Some participants were joining from their home computers. Some participants were joining even from cloud platforms with different hardware. And all of them had different accelerators with different network speeds. So one thing you can do is basically try to adapt the communication protocols you're using, like the aggregation protocols for your gradients, like ORDUs, to this setup. Not every participant has to do the equal amount of work. So if there are slower participants who cannot even accept incoming connections, you can just have them output the gradients. You can just have them send the gradients to someone else who will do the averaging work for them. So that is basically one of the ideas that can be that can be tried.
That's really interesting. Very interesting thoughts, Max. Mo, you have your hand up. I'm not sure if did you want to respond on it, or is that still up from the previous comment?
Oh, sorry. I'll get it down.
No worries. There were actually still so many things that I wanted to dive deeper in while I have you all in the space. But we are at time. So I want to just thank everyone for joining this space. I wanted to thank all speakers for sharing your thoughts. I learned a lot. These are very interesting insights. It sounds like everyone is having a lot of interesting thoughts about current research, future research, new things to try out. Very, very excited and keen to follow along all these new developments, and very happy to see so much interest and things going on in decentralized training. All right, thanks everyone for joining. Thanks for your time, and maybe till next time.
Thanks.
Yeah, and thank you for organizing.
Thanks for organizing. Bye bye, Christine.
Of course.
Bye.
Thank you. Bye.